Now next theorem is correspondence theorem. So what is the statement of the correspondence theorem? So basically the statement is, if n is a normal subgroup of a group G, then there exists a 1-1 correspondence between the normal subgroup of group G containing n and the normal subgroup of a group G by n, which is a quotient group. So the another statement of this theorem is, let n be a normal subgroup of group G given any subgroup H dash of G by n. There exists a unique subgroup H of G such that H is equal to H by n, H dash is equal to H by n. Further, if H is a normal subgroup of G, if and only if H by n is a normal subgroup of G by n. So it means there is correspondence between 1-1 correspondence between a subgroup of G containing n and subgroup of G by n. And in addition to that, there is 1-1 correspondence between the normal subgroup of G containing n and the normal subgroup of the quotient group G by n. Now, to prove this result, so first we will use the natural homomorphism. So in the fundamental theorem of homomorphism, we discuss F is a mapping from G to G by n. So this is mapping is onto, and this is a natural homomorphism. Natural homomorphism. Homomorphism. So what it, if it is a natural homomorphism, so this mapping was function f of a which is equal to n of a for every a belongs to G. So this is a natural homomorphism. And also in addition to that, also we know that the kernel of f is equal to n. So what is n? N is a kernel of f. So this is my given part. So this is a group G and this is a group G by n. And what is n? N is a normal subgroup of group G. This is a n is a normal subgroup of group G, and this f is a mapping from G to G by n. So this mapping is homomorphism, and onto. So my aim is to prove that there is 1-1 correspondence between the subgroup of G containing n and the subgroup of group G by n. So first I take two set. Let what is U? U is the set of all subgroup of group G containing n. So containing n. So it is a set of all subgroup of group G containing n, and V is a set of all subgroup of group G by N. ठीक है. So my aim is to prove that there is one correspondence between these two set G and H. There is one correspondence between these two group. Now, if I take step number one, so if I take, let H belongs to U. So H belongs to U means H is a subgroup of group G containing H containing N. Sorry, H is a subgroup of group G containing N. Now, in this step, in the first step, I would like to prove that its image is subgroup of G by N. So my claim, our claim in first step, f of H, which is a subgroup of group G by N. This is my first step. Now to prove it is a subgroup, so first it is proved that this is a non-empty. Now, as we know that E dash is equal to f of E, since H is subgroup, so it belongs to f of H. So since E belongs to H, so in that way its image belongs to this. So it means this f of H is a non-empty. Now to prove that it is a subgroup. Now to prove it is a subgroup, I take two elements. One is A and B belongs to f of H. So by definition, there exists some H1 and H2 belongs to H such that A is equal to f of H1 and B is equal to f of H2, these values. Now to prove it is a subgroup, so I need to prove that AB inverse belongs to f of H. So what is AB inverse? So AB inverse is f of H1 into f of H2 raised to power minus 1. Since f is homomorphism, so this can be written as this into f of H2 inverse. Since it is a homomorphism, so this can be written as H1 into H2 inverse. Now, H1 and H2, this belongs to H1, H2, this belongs to H, and H is subgroup. If H is subgroup, then it implies H1, H2 inverse belongs to H. It implies it belongs to H. So it means this belongs to f of h. So if this belongs to f of h, then it implies AB inverse belongs to f of h. So it implies f of h is a subgroup of group G by N. So here I prove that this f of h, which is a subgroup of group H by N. So this means it is a subgroup of group H. This is a, if H is subgroup, then its image is also a subgroup. Similarly, we can prove that if H is normal, then its image is also normal subgroup of that values, right? So that we will prove that. Now, after going to next step, so what is, we take the U and V. So I define a mapping to prove the 1-1 correspondence. So I define a mapping phi from U to V. So this mapping is defined by phi of H, which is equal to f of H, because f of H is a subgroup of G by N. So I define these values for every H belongs to this capital U. Now, first phi is well defined. So first prove it is a well defined mapping. This is a well defined mapping. So I take H1 and H2 belongs to U such that H1 is equal to H2. So clearly it implies its F image, F of H1 is equal to F of H2. So it implies phi of H1, which is equal to phi of H2. So this is by using the definition of these values. If it satisfies, then it means this mapping is well defined. So we prove that this defined mapping is well defined. Now next is, it is a 1-1 and then it is a onto. So to prove the 1-1, so let phi of H1, which is equal to phi of H2. So what is H1 and H2? It belongs to U. It means it is a subgroup of G containing N. If this values, so it implies f of H1, which is equal to f of H2. So this is by definition. Now my aim is to prove that H1 is equal to H2. So what is our claim? H1 is equal to H2. So to prove this H1 is H2, so I take some element H1 which is belongs to capital H1. Now this element belongs to H2, then H1 is a subset of H2. And similarly H2 will be a subset of H1. Now from this, if I take H1 belongs to H1, so it means f of small h1, which is equal to, which is belongs to f of h1. And what is f of h1? This is equal to f of h2. So this element belongs to, this element belongs to this set, if this element belongs to this set, so we can write it as f of h1, which is equal to f of h2. This is for some element, for some h2 element belongs to h2, this values. Now, this can be written as f of h1, f of h2, and this is -1, which is equal to e dash. So this is the identity of right hand side. If it is the identity of right hand side, now since f is a homomorphism, so this can be written as f h1 f of h2 inverse, which is equal to e dash. This is equal to f of h1 h2 inverse is equal to e dash. If this value is equal to e dash, then those element whose image is identity, that element belongs to kernel of f. So h1 h2 inverse belongs to kernel of f. So what is kernel of f? Kernel of f is n. Now n is a subset of h1 as well as h2. So it means this is a part of h2. So this is a part of h2. So it implies h1 h2 inverse is part of h2. Also h2 belongs to h2, and h2 is a group. If group, then it is closed under scalar multiplication. So it means h1 h2 inverse into h2 belongs to h2. So it implies h1 h2 inverse into h2 belongs to h2. Since it is a identity, so it implies h1 belongs to h2. So h1 is a element of h1 and it belongs to h2. So it implies this h1 is a part of h2. So write it as equation number 1. Now on same line of action, yeah, we can say similarly. So similarly, H2 is a part of H1. So this is equation number 2. Equation number 2. So from 1 and 2, it implies H1 is equal to H2. So it implies this mapping phi is a 1-1 mapping. So this is a 1-1 mapping. Now to prove the onto, so this is a 1-1 mapping. So to prove the onto, so I take one element h dash which belongs to V. H dash which belongs to V. So my aim is its previous image, its phi inverse h dash, its previous image is a subgroup of G containing N. Now, so simply our claim, F inverse H dash which belongs to U. This is to prove the onto. My claim it belongs to U. So what is U? U is a subgroup of G containing N. so that I want to prove that if it is a subgroup of group G, such that in that case phi of this image is equal to H dash. So to prove this result, I take two elements A dash B dash, so which is equal to F inverse of H dash, this values. What it implies? It implies F of A, F of B dash, it belongs to H dash. So what is H dash? So H dash is a subgroup. So by definition of subgroup, this is F of B dash, this minus belongs to H dash. Again F is homomorphism, so this can be written as A dash B dash inverse belongs to H dash. So this means A dash B dash inverse belongs to F inverse H dash, this values. So it means it is a subgroup of group G. So this is a clearly, if this part satisfied, so it implies F inverse H dash, which is a subgroup of group G. Now second is it containing the N. What is N? N is a kernel of F. So to prove it containing the N, so as we know that let X belongs to N. So what is N? N is kernel of F. It implies F of X is equal to E dash, right? So your F of X equal to E dash. So if it is F of X is equal to E dash and E dash is identity and E dash is identity, identity is always belongs to its subgroup, belongs to subgroup. So E dash belongs to H dash. It implies this X belongs to F inverse H dash. So it implies F inverse H dash, which is a subgroup of group G containing N, right? It implies F inverse H dash, which belongs to U, which belongs to U. It means for every H dash belongs to V, there exists F inverse H dash belongs to U such that phi of F inverse H dash, F inverse H dash, so this is equal to F of F inverse H dash, and this is equal to H dash. So every element of V has pre-image. So it implies this phi is mapping onto. So this phi is mapping onto. So it means there is one correspondence between U and V. Now, to prove the normal subgroup, mean if group of U is normal, then if the subgroup of G is normal, then its image is also normal in G by N. So step number 3, so let H be a normal subgroup of group G containing N. So containing N. H is normal subgroup. Now here it is a normal subgroup, not simple subgroup, normal subgroup. So our claim, its image is f of H. So what is f of H? So this will be H by N. So this is a H by N. So this is a normal subgroup of group G by N. So that is my claim to prove this result. Now, if I want to prove this result, so first let H is a normal subgroup. To prove this is a normal, I take let Ng, so it belongs to G by N, and N X N H, it belongs to H by N. So it belongs to H by N, where G belongs to capital G and H belongs to capital H. So to prove the normal, so what is Ng inverse NH into Ng? This can be written as Ng inverse NH Ng. Since it is a product of right coset, so that is again coset G inverse Hg, this values. Now from this, G and H belongs to G, H belongs to H, and H is a normal subgroup of G. So it implies G inverse Hg belongs to H by using definition of normal subgroup of H in G. So this element belongs to H. If this element belongs to H, then total element belongs to H by N. So this is by this element. So it implies this H by N is a normal subgroup of G by N. So it implies this F of H, which is a normal subgroup of group G by N. Now this is first part. So if element of set of U is normal, then its image is normal. Now in reverse part, if the element of K is normal, then its inverse image is normal. Now I take let K, which belongs to V, and it is a normal subgroup of group G by N. So this is a normal subgroup of group G by N. So K is a subgroup of G by N. So we directly write it as K is a normal subgroup of G by N. So my aim is here its inverse image, which is F inverse K. So if I take K, then its inverse image is normal subgroup, normal subgroup of group G containing 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 N. So this is my aim. So just write the element of F inverse K. So to prove it is a normal subgroup, if to prove it is a normal subgroup, let I take G is belongs to capital G, this, and X is some element belongs to F inverse K. So what it means? It means F of X which belongs to K. It means this values. F of X belongs to K. Now as G belongs to capital G, then it implies NG, the F of G, its image, it belongs to G by N. So K is a normal subgroup of this G by N. If K is a normal subgroup of G by N, so it implies F of G minus 1, F of X, then F of G, it belongs to capital K. Now it implies, since F is homomorphism, so F of G inverse, F of X, F of G, it belongs to K. Since F is homomorphism, so this value is G inverse XG belongs to K. It implies G inverse XG, it belongs to K. So what we get? We get K is normal subgroup. Normal subgroup. Now second part, it containing N. Now second part, it containing N. So let X is some element belongs to N. So what is N? N is kernel of F. If N is kernel of F, so it means F of X which is equal to E dash. And what is K dash? K dash is a subgroup of group G by N. So it means E dash belongs to this because it is identity. So it implies F of X belongs to K dash, and it implies X belongs to F inverse K. Sorry, it is a K, not K dash. It is a K. So F inverse K. So it implies this N is part of F inverse K. So what we get? We get there is 1-1 correspondence between subgroup of U and V, and also there is 1-1 correspondence between normal subgroup of G containing N and normal subgroup of G by N. So this is a 1-1 correspondence between normal subgroup of group G and subgroup of group G by N. So this is a correspondence theorem.